All right. Hi, everyone, and welcome back to the Theory of Computing for Fairness seminar series. So today our speaker is Chara Podimata. She is right now an assistant professor of OR and stats at MIT. She's also a lead researcher at Archimedes Athena. She's working in like a lot of different things. She's been working on theoretical computer science, economics, machine learning, incentive-aware mechanism design, machine learning, social computing, online learning, like quite a few different things. Also, recently she started like thinking about policy questions that are related to AI and to recommendation systems. Today she's going to tell us about her work on strategy consumption and altruistic engagement. And Hara, take it away. It's all yours.
Thank you, Juba. Thank you, everyone, for being here. So I'm going to be talking about from strategic consumption to altruistic engagement. This is a game theoretic view on recommendation systems. And this will be a synthesis of two papers that I've written with a set of wonderful collaborators. Kat Fedorova, Andy Help, Dylan Hadfield Manel, and Madeline Kitsch. Kat is my PhD student, and Madeline was my pre-doc. She's now a PhD student at CMU. And Andy and Dylan were my collaborators before I started as an assistant professor at MIT. So before I delve into the specifics of this talk, and by the way, just letting you all know that I have a lot of slides, I have a lot of content for today, so I would very much prefer this to be a discussion rather than me going through all of these slides. So if we don't finish the slides, that's fine. I think the main message of the talk is kind of like understandable after like slide 5 or so. So we will for sure reach slide 5. Okay. So before I delve into the specifics, I wanted to give you a brief overview of how all these different topics that Juba mentioned, they tie together, and what is the unifying theme of my research agenda. So I think a lot about algorithms, algorithms as constructs, both from a theory point of view, standard linear regression classification algorithms, but also algorithms that govern more complex black box systems like recommendation systems and very recently large language models, LLMs. I think of algorithms as decision-making devices for humans. So they get human data from different individuals, and they give back to these individuals certain outputs in the form of, information from the LLM after a prompt that you gave, or recommendations from an algorithm, or sometimes decisions. For example, if you apply for a loan, the algorithm tells you whether you got the loan approved or not, whether you will get hired if this was like a hiring algorithm, or whether you get, certain benefit allocations. Now, because of the fact that these decisions critically affect humans' lives, there ends up being a feedback loop where the algorithm's decisions themselves have direct effects to society. And because humans understand by now these effects and they understand how algorithms govern their everyday lives, they oftentimes strategize or they try to adapt to these algorithms themselves. So my research studies different models of human adaptation to this sort of pipeline. I have listed some here. I have thought a fair amount about best responding myopic agents that just think about, one step ahead or even like the current present step. I've thought a lot about long-term non-myopic strategic individuals thinking about how their present decisions will affect critically whatever they receive in the future. And I have also thought about how sometimes you may have unpredictable or irrational agents. And very recently, as Juba mentioned in the introduction, I've come to realize that although I'm a trained theoretician, a lot of the questions that we're grappling with in this like human in the loop of algorithmic decision making pipeline will not just be solved with our theoretical toolkit. So I've started thinking a lot about affecting policy decisions and regulation through opinion pieces and op-eds. So to summarize my research agenda, on the one hand, things about how do we design better algorithms for, outputs that or decisions that are robust to strategizing or they learn how to adapt to strategic individuals. I also think a fair amount about quantifying the effects of algorithmic decision making to different subpopulations. And then last but not least, I've started thinking a lot about auditing policy and influencing regulation in algorithmic decision making. And although I'm a trained theoretician, as I said, in the last 3 or 4 years, I've started using a lot more social science experiments in order to ground my theoretical models. And the byproducts of the theoretical models sometimes end up creating policy or so policy suggestions or opinion pieces. I have here a slide that gives you a brief overview of the types of topics that I've thought about: fundamental machine learning tasks, robust to strategic individuals, some more specific things about the design of online platforms. Very recently, and this is a very theoretical work as well, we've started thinking about how to do optimization of large language model inference and fairness and auditing, which will be, I think, the core interest of this group over here. Before I delve into the specifics of the theoretical part of my work, I want to highlight something with regards to fairness on auditing that I've been super excited about lately. And I know that this is a theory audience, so maybe you're not going to be this interested, but bear with me because I think this is super fun. So I know that all of you know that large language models are influencing everything that we do right now, and everyone and their brother wants to work on large language models. What we started thinking about in the lead up to the 2024 US presidential election was the following question. What if people start getting more and more information about their elections from large language models? We don't have any concrete data set that tells us what these models are doing or that explains to us how the models were giving different information to different individuals. I mean, the US presidential election 2024 was the first big election after the soaring popularity of large language models. So my team of collaborators and I set out to study exactly this question. How were large language models as mediators of election information? We collected a data set for roughly 4 months and almost daily from July to November 2024. We collected a structured survey of more than 12,000 questions that we were asking to 12 models, leading up to the US presidential election. And we have released publicly the data set now, and we have released our first analysis as well. So yeah, if you're interested in also thinking about these questions, please read this paper. You are free to download the dataset and run your own analysis. And I'm also happy to discuss with anyone who is interested. We're currently gearing up for running a version of this, a bigger version of this study for the midterm elections. And we've been in collaborations and talks with political scientists and election officials about the types of questions that they would want to see in this questionnaire. I will pause here for 5 seconds if there are any questions or
Not,
anything.
not a question, but I'll ping you on Slack. I'm interested.
Okay. Okay, good. So back to recommendation systems, which was the thing that I advertised that I would talk about today. Um, so recommendation systems create a feedback loop. And here, when I talk about recommendation systems in this talk, I don't want you to think about a single recommender system. So I'm going to try to abstract away from anything specific, but recommendation systems exist behind, YouTube, Netflix, TikTok, Instagram. Almost everything in our daily lives is governed by some sort of like a recommendation system. Now, what is the feedback loop that I outline here? Well, on the one hand, you have the user. The user, sorry, interacts with a recommendation system, let's say TikTok. And how does the interaction happen? Well, the user consumes content or interacts with content, engages with content. These are three different verbs that we usually see associated with user behavior and recommendation systems. based on what the system has already recommended to them. So you go on TikTok, you see a set of, recommended videos or whatever, and then you click on the one that you want to see. Or to be more accurate for TikTok, it's more of a like real-time decision where, TikTok serves you a recommendation and then you decide whether to linger and watch it fully or like scroll past it. Now, the recommendation system itself, based on these interactions, based on whether you stayed on the video, how long you stayed, did you go to the content creators page, um, they change what they recommend to you in the future. And this is something that is very personalized. This personalization is a feature and a bug of recommendation systems. And in the policy circles, this is what people sometimes call, the process of curation has now become a form of creation. Because, originally you would only curate your own recommended content, but now, based on what content you curate for yourself, it ends up creating a micro world in which you exist. And it affects critically the types of contents that you're exposed in the future as well. The critical key assumption here when it comes to the literature in recommendation system has been that the user themselves is static, which means that they consume content kind of myopically, which means that, whenever they get served something from TikTok or whichever other recommendation system, they choose to interact based on whatever they like in that particular moment. I want you to remember the word static. It means basically that there's no other considerations at the back of the mind of the user when they're interacting with content. Now, although this has been the prevalent theoretical assumption when it comes to recommendation systems, and also the technical assumption when it comes to engineers building these systems, human-computer interaction studies document a very, very different reality. And here on the left and bottom footnote, I have some studies from, core HCI members that have appeared in the biggest HCI venues. But I also have on the right some citations from the papers that we have written in the area, because we have also run human subject studies trying to understand how they interact with recommendation systems. So some choice quotes that we've seen from HCI studies are the following. If you like a certain post with certain hashtags, then they start to show more of that content. So users have started building a folk theory about what the system is doing, and this affects what they do in the future. Okay. And this is the first message that I wanted to drive to this audience, an audience of mostly theorists, is that whenever you want to think about a specific real world system and you want to model human behavior, we really need to start thinking about, instead of just positing random behavioral models that are useful to us from mechanism design or whatnot, we really need to spend the time like doing these social science experiments where the way that I've been doing them is I create surveys and then I survey a large part of the population online and try to deduce from their responses the types of behaviors that they exhibit. And then once you have a collected data set of these types of responses, you can like distill it into first principles, into a model that you can work with. We're going to see this process in a couple of slides too.
All
Yeah.
right. Let me ask you a quick question. So when you're doing this, you're not directly choosing your participants, right? You're kind of like getting them potentially randomly online. Or
So we have used, you can do that too. What we have been using is Prolific mostly. Actually, for the first study, the one that is on Archive 2023, this is done on Amazon AWS. The second one is done on Prolific. So I don't have access behind how Prolific is recruiting their individuals, but I know that you can create certain demographic quotas that you say that, hey, I want this much breakdown in terms of like race, gender, and whatnot.
Mhm.
Okay. So the main questions that I want to address in this talk today, and these are the questions that both of the papers have addressed in different capacities, is, this seems to be like a very pesky problem, very complex. So how do we theoretically model the dynamic user behavior in recommendation systems? That's question number one. Question number two, can we theoretically understand why users behave this way? So is it something that, the system itself, the recommendation system is incentivizing? Because once we understand that, then we can have some hope about mitigating this behavioral problem with these users. And then ultimately, I want to understand and study the downstream societal effects for different subpopulations of users. So if users do adapt to what the recommendation system is serving to them. Do all subpopulations need to adapt in the same way? Well, sneak peek, the answer is no. Minority subpopulations end up needing to adapt way more so that they don't get completely erased by the recommendation system. And then this creates like a snowball effect of how do you quantify these like downstream effects and how do you mitigate them? Basically, all fun fairness questions arise in point three of this interaction. Okay. Um, so the two types of user behaviors that I'm going to highlight in this talk, and they were also obvious from the title of the talk, are on the one hand, selfish and strategic users, and on the other, altruistic behavior. These are not the only types of user behaviors in recommendation systems. These are the ones that I have found to be very fascinating and I have worked on right now. So what do I mean when I say selfish or strategic user behavior? Well, I will call users selfish or strategic when they consume content with the purpose of steering the algorithm to give them a certain type of content in the future. And I have bolded here the word them. So this is all about what the algorithm is doing with regards to the same user themselves in the future. So let's see an example of the user studies that I run for selfish or strategic agents, and it will give you an idea for the types of behaviors that users engage in order to convince the recommender system to give them some sort of content in the future. So people responded to my survey things like, I like stuff just to see more of that type of stuff, even though I don't like it. Like sometimes if my content gets too dark, I try to like animal videos and comedy more to get off the darker content for a bit. So here we see a very, very clear example of a behavior that someone is doing because not because they like it myopically right now, but because they're trying to steer the algorithm, they're trying to give a signal to the recommendation system algorithm about what they want to see more of in the future. Another type of like selfish or strategic behavior is people that tell us that they are cognizant of what category of video they think material falls under. I'm careful to watch completely videos that fall under the correct category, even if I'm not interested in that particular video. If I'm careful to skip over videos from the wrong categories. Another classical example of very specific strategization within the context of recommendation systems. The second behavior that I want to highlight in this talk is what I call the altruistic content consumption or the altruistic engagement, where users consume content to steer the algorithm to boost a certain type of content for others. This is the behavior that we studied in the second paper, the one with Kat and Madeline. From the user study that we run from that paper, we got responses like, I just do this, interacting with this particular content to support creators and help them grow. We see that there is this like classical component of, sure, this is not just about what I like, but also how can I influence the algorithm to give more of a certain type of content to other people. Or I remember seeing a woman raising money for a personal cause. I intentionally interacted with her TikTok post by liking, sharing, and leaving supporting comments. By the way, this is a behavior that we've seen a lot of in what people call book talk, which is the subworld of TikTok that focuses on promoting certain types of books. We saw a lot of this like altruistic consumption or altruistic, boosting of content during the Black Lives Matter protests. And we've also seen a fair amount in the past 2 years where people sometimes go under political videos, and they comment things like, oh, this is a great makeup tutorial, or this is a great hair tutorial, because they're trying to, convince the algorithm that this was a video that would be applicable or interesting to mainstream population, and so the algorithm should recommend this video to more people. Questions so far about the two types of user behaviors that we're going to be focusing on? Okay, so I want to create a modeling framework for thinking about these types of questions. And for now, I'm not going to constrain myself into thinking specifically about strategic agents or altruistic agents. So for now, just ignore the specific behavioral model that makes users behave one way or the other. I will be using a version of Stackleber Games, which is a two-player game. So the recommendation system originally commits to a recommendation strategy. This can be something like a top K. So the recommendation system may announce to the user that, hey, if I have collected a set of, ratings or a set of engagement from you, I'm going to be recommending the top K items from this engagement matrix from now on. Then nature collects a true ratings matrix. I'm going to denote this as R star of M agents or M users. I'm going to use the terminology user and agent interchangeably for N items. What is the ratings matrix? Well, the ratings matrix can encode, and I'm using here recommendation systems terminology, but you should think of it as like a preference matrix, right? So it includes things that can be quantifiable, like the watch time for a person for a video that they were exposed to, the number of playbacks, because we know that sometimes people just replay the same videos, the number of comments that a person has left under a video, or the number of likes and shares that they've done for a certain video. And at a second stage, the agents report a revealed preference matrix that can be potentially different than R star. Okay, so the revealed preference matrix, you should think of it as like the true interaction between item one and user M. And here I'm making this kind of like mechanism design analogy, mechanism design connection, where I'm saying that, look, there's a true ratings matrix, a true preference matrix that corresponds to how fundamentally the user likes a certain item. You should think of items as like videos if we talk about TikTok. But the user is not gonna always reveal the true preference. They're only gonna reveal like a reported matrix R tilde. Okay? And there are several ways I'm making the abstraction here. I'm making several abstractions, but one is that the user comes out of the door and says, announces to the learner, announces to the recommendation system, hey, this is my matrix, my revealed preference matrix. So this is, if you measured everything correctly, this is exactly my watch time for video one, my watch time for video two, and so on and so forth. In reality, there is a lot of like learning and matrix completion happening under the hood over here, because the interactions do not happen all at once. So the recommendation system needs to collect different interactions and then build this matrix from scratch. Okay, so now that we have verified, we have confirmed what the agent does, the recommendation system collects the revealed preference matrix. They do something. I'm not going to tell you what right now, but they ultimately decide that, hey, based on your revealed preference matrix and based on my own objective function as well, which for the purposes of this talk, I'm going to assume that the recommendation system cares about, maximizing social welfare. I'm just going to recommend to you your top item, top U. So ultimately, the social welfare for all the agents is the sum for all the users, all the agents, R star, U, and top U. Now, two things I want to note here. Actually, I want to note one thing. The social welfare is measured with regards to the true preference matrix, R star, okay? But top U, the item that's ultimately recommended, is defined with regards to the revealed preference matrix, okay? Good. I want to zoom in on the recommendation system because I haven't told you what the recommendation system does and how they go from the revealed preference matrix into defining what item they should recommend to the user. So in the paper, in the Archive 2025 paper, we define what we call an alpha loss tolerant learner. This is our own defined abstraction for how a recommendation system operates, and it is meant mostly as a theoretical construct that can help us abstract away from what is the exact recommendation system algorithm that's used. Like, I don't want to have to think about uh, exactly what TikTok does versus Facebook versus Instagram. I want something that seems to capture reality closely, while I know that's missing a lot of, details. Okay, so the recommendation system receives the revealed preference matrix or the revealed ratings matrix R tilde, and then computes another matrix, which we call R hat, and it's the K star truncated SVD of R tilde. This tries to capture the spirit of collaborative filtering over here. Um, and how does this like K star truncated SVD happen? Basically, you minimize K, you try to minimize the rank such that the singular value SK plus 1 of R tilde is upper bounded by alpha. Basically, this is our abstraction that helps us go from R tilde into a rank reduced approximation because the learner, the recommendation system, cannot keep track of all the information in the ratings matrix. Like, they always need to do some sort of rank reduced approximation so that they can very fast and very easily recommend content to different users. At a high level, the interpretation here is that the resulting matrix R hat is analogous to learning for the recommendation system. It's as if the recommendation system itself had a hard time learning part of the preferences that were very unique. So think of it as like you didn't have enough information from the revealed ratings matrix. So I have created an abstraction here that tells you that, hey, if you did some sort of like matrix completion, you wouldn't have enough information to deduce what happens for certain parts of the matrix. So putting everything together, from the user side, we have this process where the recommendation system has committed to a recommendation strategy and it's announced to the user. The user knows their true ratings, their true preferences for the different items, but they choose to report a revealed preference matrix R tilde that is potentially different than R star. On the other hand, we have the recommendation system itself, which receives R tilde. This is the revealed preference matrix. They compute R hat, which is the K-star truncated SVD of R tilde, and then gives each agent their top item according to this R hat. Okay? Questions here? Okay. So I want to zoom in for a second on this part here, because this is the crux of the behavioral model for the agents. I haven't specified to you at this point how do the agents decide to report different revealed preferences. Okay. And so if agents were to be strategic or selfish, they would choose something that would make it so that at the next round, the recommendation system would give them exactly what they want in terms of, their self-interested utility. If they were altruistic, then maybe their utility would be more, like thinking about different parts of the population. So they would change their revealed preferences in order to make it so that the recommendation system would take some other actions with regards to maybe more minoritized content or minoritized identities. So, question here, why would the users ever be incentivized to report something that's different than r star? The fundamental problem is that recommendation systems nowadays have millions of users. Sorry, I said students. I just came out from my 3 hour teaching. So students are at the forefront of my mind right now. But going back, the fundamental problem is that the recommendation system has imperfect and coarse information about the users, but also about the items that the users interact with. So think about it like that. How many videos exist right now on TikTok? And how many different categories of videos exist on TikTok? There are millions, maybe billions of videos on TikTok. It's like virtually impossible to maintain a matrix that has the exact true ratings for each user for each different video or even each category of videos. So part of, the feature and the bug of recommendation systems and collaborative filtering is that they have to, obtain imperfect coarse information and make generalizations for other, you make inferences for other users that look like the users that, the user that, they think you are. To put it into perspective, imagine that in real life, there's only like three types of videos that you can be exposed on. There can be like NFL, there can be dog videos, or they can be, the Kardashians. And when we go from left to right, is so like you like the NFL the most. The second most favorite thing is dogs, and the third most favorite thing is Kardashians. Now, what this means is if you could give all the information about yourself and your preferences, you could probably say something like, I'm a sporty spice, but I also really like dogs, and then the Kardashians are my guilty pleasure. The problem is that because of the fact that the Kardashians, for example, is very mainstream content, there are a lot of people that really like them and watch them, not just because it's their guilty pleasure, but because they fundamentally like them. If you started liking videos or like watching videos from the Kardashians, it would very, very quickly overpower your TikTok algorithm. This is something that people have noticed. This is the reason why, sometimes when they want to consume content from what they think is a mainstream channel, they sometimes go in incognito mode or something like that. So let me focus on altruistic users first when it comes to the behaviors that they exhibit. So altruistic users, are they ever incentivized to report ratings truthfully? And the answer is no. And I'm going to show you why they are not incentivized to report truthfully. So let me assume that the entire population of users is split into majority, minority subpopulations. And so all the matrix, the true preference matrix are matrices are star that I'm going to be focusing on, have this property of being majority, minority matrices. And I'm going to define precisely what a majority minority matrix is in a second. But basically, when your matrix R star, the true preference matrix R star, is a majority minority matrix, then altruistic users report what we call correlated strategies to improve the agent's social welfare. Roughly speaking, what this means is that there's a movement that helps users understand how to report in terms of the revealed preferences, and they kind of understand that once they do that and they are coordinated in how they like videos and how they like forward them to friends or like they comment under the videos, then it actually ends up changing how this video gets recommended to different users. So let me give you the definition of majority minority R star and majority minorities of populations in the process. So majority minority R star matrices are matrices such that any like a reordering of the rows and columns results in the type of matrix that I have here on the right. This means that you have a majority of users that really like the first, I don't know, M prime items, and they really don't like any of the other items. And the minority users are completely flipped. So they don't like anything in terms of the majority items, but they do like a lot whatever happens in their minority items. Roughly speaking, what this means is that I have a perfect separation perfect separation between what the majority users like and what the minority users like. So in the previous example that I had with the Kardashians, that example is not captured here because most probably it would be the case that, the majority users would include a preference for watching a Kardashian video, but the minority users would not have this intersection of preferences at all. And if you think to yourself right now, hey, Hara, this is like super restrictive, I agree. I wouldn't say that it's super restrictive, but it's kind of restrictive. And in the paper, we generalize that to have small intersections between the preference profiles of the different users. But for the purposes of this talk, let me just ignore this, like shove it under the rug. Okay? So the assumption when it comes to these types of matrices that I'm going to make is that there exists a singular value gap, that there exists a singular value gap. So the matrix is such that this jth singular value for the majority users is greater than the first singular value for the minority users. And this roughly means, as I said earlier, that if you have your entire population here, then the population is segmented into two parts. And it's perfectly segmented in two parts. Part number one is the cat lovers. These are like groups of the population that only, may like cat videos or cat content. And then you have dog lovers that may only like dog videos, and they don't really want to interact with any other type of videos. Any questions so far? Sorry, I don't know why I did this. I was trying to access the videos of people, but it ended up. Can you see my screen now? Sorry.
Yep, it's working.
Okay. Yeah, I can't see the videos anymore, but that's fine, I guess. Let me let me see if I can see. Yeah. Okay, never mind. Okay. So I want to comment on the social welfare that our algorithm that, standard recommendation system algorithms obtain under truthful rating. And by the way, note that here I'm going to be using the model that I had earlier. So I'm going to try to make claims about general recommendation system algorithms. I'm not going to constrain myself into the specific recommendation system algorithm behind TikTok or Facebook or Instagram, whatever. The only thing that matters is that I will be using this alpha loss tolerant construction that I have, the alpha loss tolerant construct, and this is how I'm going to be arguing in terms of, the social welfare and the different ratings. So let's imagine that our population is again split into cat lovers and dog lovers. These are the only two subpopulations that I have. And imagine that the cat lovers are actually the majority subpopulation. What ends up happening is that the cat lovers, they end up getting their most preferred content, which is a content videos about cats. But because of the fact that the recommendation system does not have enough information about the dog lovers, they end up recommending cat videos to dog lovers as well. And this is a phenomenon that we actually see happening in recommendation systems a fair amount, and a lot of people are complaining on TikTok about it. When they have more niche interests or they belong to communities that are not as mainstream, then the recommendation system ends up shading their identities completely. Now, through our model, we can formalize that and understand why this happens. If you end up reporting truthfully, if R tilde is exactly equal to R star, and the majority population has stronger tastes or is more prevalent in your data set, then all majority users get their top item, while the minority users are given a majority item they do not like. So this basically tells you that if minority users chose to truthfully report their preferences to the recommendation system, the recommendation system, just by virtue of the fact that they will have to do some rank reduction, they will end up misrepresenting the minority users' preferences. And the proof idea here is very easy to understand. So imagine that you have, this is your standard, the R star, as I mentioned earlier. This is a majority minority matrix. This part, the left part of the matrix, is rather information heavy. This means that there are a lot of interactions, there are a lot of users. The recommendation system, when it has a matrix like that, prioritizes whatever happens over here because it has a lot more information for the recommendation system. On the other hand, the minority users, they don't provide a lot of information to the recommendation system. So this is information light. And so when the learner or recommendation system, they have to rank reduce, they will end up throwing out dimensions that have low information for them. So this is how information about minority preferences ends up getting lost. So it's not a matter of like a specific algorithm. This is kind of like a baked in property of collaborative filtering and of rank reduction. And I have it here also in more mathematical terms for those of you interested. So how can we improve social welfare now that we know that, truthful reporting is not helpful for minority users? Well, we know that the dimension constrained learner's optimal reduction keeps only this part because it doesn't have information about other parts of the matrix. But majority users, when they engage in altruistic behavior, they are trying to force the same learner, the same recommendation system, to learn some of these smaller hidden preferences. So we define a class of strategies called altruistic reporting, which resembles what happens in practice, although abstracts away from how exactly users achieve that. What we say is that, look, the majority users, they are gonna now become altruistic users, and they're not gonna change their main preferences over here at all. Okay, so this part of R tilde does not change at all. What they will do is they will lie a little bit to the recommendation system and tell to the recommendation system that, hey, I like this item a little bit, okay? I don't like it nearly as much as my like top preferred items, but I also don't like it to a zero extent. We call this the collective of altruistic users operate for some minority preferred item by eta. And we have a bunch of generalizations in the paper about how many users are needed to operate, by how much do they need to operate, and do they need to operate to an extent that goes closer to R tilde or not. But the bottom line is that this provably actually helps the minority users get some of their preferred items from the algorithm. So we construct in the paper the sufficient conditions for what we call effective altruism. We construct the sufficient conditions for this operating mechanism to be successful such that the minority users do not get completely erased. So if the original R tilde is exactly as R star, we have this property when it comes to like the singular values. Now consider an eta UA. This is the set of users that are participating in our altruism movement. They are operating something that I call a picky item I star. This is the first item that's mostly liked by minority users and not liked at all originally by majority users. Then we show that the social welfare is improved if one, the eta, the uprating that the majority users do, is above zero, of course, but is also upper bounded by a quantity that roughly says that it's not too high that the learner learns to recommend this strategic item to altruists. Okay, so we have to be careful here because we want to design strategies that don't make the altruists better off. Sorry, don't make the altruists worse off when it comes to their own personal recommendations. We want to design strategies that the altruists are exactly as good as they were before, and now they're also helping the minority users as well. And the second property here is roughly saying that eta needs to raise up the singular value sigma 1 of the R star minimum so that the learner is forced to retain an extra dimension. What does it say roughly here? It says that, look, if you have a recommendation system that will tell you that I'm not going to tell you exactly how many items I'm going to keep in my rank reduced approximation of the preference matrix, I'm going to tell you that the algorithm that I use or that the process that I use is that I keep the quote unquote most informative items. Now, if the most informative items are 10, I'm going to keep 10. If the most informative items are 15, I'm going to keep 15. This is defined by this like tuning of alpha that we have over here. And this seems to be also how recommendation systems algorithms work in this space. So what we're saying is that, look, if the recommendation system commits to this sort of like alpha loss tolerant property, okay, then I can kind of like force the recommendation system to keep one more item in its rank reduced approximation so that the minority users are satisfied because they get at least one item that they really like and they don't get completely erased. Now, what about the recommendation system itself? Is it good algorithmic design to incentivize altruistic collective action? And the answer, and this surprised us, is actually yes. So, for majority minority matrices, when the agents end up operating with a process that I said before, if you have a population that's split into two, cat lovers and dog lovers, you end up increasing the social welfare strictly because you now have a population of dog lovers that was previously not getting any of the items that they wanted. Now at least they get at least one item that they liked. So from a social welfare perspective, you really like that as a recommendation system. Now let's think about an engagement metric where recommendation systems care a lot about how many clicks and likes and comments, generally engagement is generated in their platform. So by allowing users to have this altruistic collective action, you end up making users spending more time upgrading other items. So also from the perspective of an engagement-based recommendation system that doesn't care about social welfare, but it cares about, engagement on the platforms, we do see that that helps engagement for the recommendation system itself. So this also provides an explanation to all of us about, okay, if the recommendation system fundamentally incentivizes collective action, why haven't people or companies done a better job like cracking down this type of collective action? And the reason is this: I think that companies are thinking that they either can obtain more information about minority users through altruistic actions, or they are just purely selfish themselves and they understand that this is like generating more engagement for the platform, and that's what they care about. In the last couple of minutes, and I will give some time for questions as well, I want to talk about strategic and selfish users. And specifically, I mentioned earlier that there's going to be a disparate impact of selfish or strategic consumption. And I kind of highlighted it earlier as well, but I want to delve more deeply into it. Imagine that I have three content types. One that is majority preferred, this is the NFL. One that is what I call minority preferred, this is the dog content. And then there is something in the middle. Note that, by the way, this is different preference profiles from what I had earlier in the majority minority matrices, because there was no intersection between the content that the different subpopulations like. But here there is an intersection, and that is the content that's the mainstream. And in the paper, We also have specific consumption preferences that tell you that the majority population essentially consumes primarily majority content and a little bit of the mainstream content, that's the Kardashians. On the other hand, you have minority users that their true preference is to consume a little bit of the mainstream content, but primarily minority content. In many reasonable equilibria for the recommendation system, it ends up being the case that the strategic user's revealed consumption to the recommendation system needs to be this. So they need to shade completely their mainstream preference, their preference for the mainstream content. And this happens out of fear that if they start interacting with mainstream content, even by a little, their identity will be completely erased and the recommendation system will completely miss this part of their identity. So I had some explanations about why this is an equilibrium, but since I'm running low on time, I want to just directly jump into the implications for the minority here. So what do we see for these types of equilibria that, again, they are fairly natural equilibria that arise as a result of a recommendation system being, a social welfare maximizer, but that doesn't have enough information about the underlying users. We see that there is not a cognitive load for majority users. So majority users, they exhibit no need to strategize. There is no cognitive load that they need to spend. They can just like go on the recommendation system and enjoy the content that is given to them. On the other hand, minority users, they do have a lot of cognitive load to manage, and they also end up acting more what I call stereotypically. What I'm trying to say here is that there is one part of their identity that is really important, and that's the minority preferred content. And they only consume this. They don't consume anything that's in the intersections with the majority population. And they show some mainstream abstention, which ultimately results in worse echo chambers. So some things that we saw and verified that in our study that we did with real humans was people telling us that I make sure to interact with things that are specific to the content types I want to see, even if I don't really like the content of that specific video. This is a direct byproduct of people wanting to make the system understand that this is where it should be focusing rather than, the specific video or whatnot. Or people were telling us that they would use to search things that I wouldn't want recommended to me, stuff that I like, but stuff that I wouldn't want to clog my feed. Another example of, if you have a mainstream content that you're afraid that is going to clog your feed, then you're very wary of not searching it and not consuming it as a real user. So that was about it for my talk. I wanted to bring to your attention that, there is this feedback loop that exists between users and recommendation systems. There's plethora of user behaviors that we see that are by far not static. And I feel that this group here has the tools to address non-static user behavior in these systems. And we also have the potential to study the downstream societal effects for different users or populations in these systems. Thank you so much.
Thanks a lot, Hara. Yeah. Well, I mean, we have a tiny bit of time, for we have 2, 3 minutes for questions. So if anyone has a question, you can go ahead. If you don't have a question, I actually have one, but I'm happy to wait for a second. All right. Well, I guess I'll go ahead and ask.
Mhm.
Does do you have a sense or understand at all in real life, like what fraction of the users are actually being strategic on like a platform like this, like say TikTok or Instagram?
I don't know what happens in terms of like internal things. I can tell you that from our study on AWS 2 years ago, out of our respondents, roughly 70% of people told us that they strategize in one way or the other, which was a huge surprise to me because the population that we surveyed used skewed older compared to the population that actually exists on TikTok. So I
Hmm.
think that it's very, very prevalent.
Okay, that's very interesting.
Yeah, I found it strike. I didn't believe that it would be like 70%.
Yeah, no, that's a lot more than what I expected. It's also kind of insane because I'm like I to some extent I feel like a lot of people don't even understand how the algorithm kind of like works, right?
Yeah.
So the fact that like so many people are actually kind of like trying to strategize is super interesting.
Yeah, and I mean, there's a lot of HCI studies that talk about um, how people obtain information and they build folk theories around these algorithms. So, and that's also fascinating.
Makes sense. Yeah, no, that was super interesting. Well, I think if we don't have other questions, it's 1 p.m., so I'm happy to end here. But Hara, thanks again for the talk.
Thank you.
We'll see
Bye.
everyone soon.